This video is my first video in a series about buffers, and we're going to start out with just qualitative background and the idea of how you make a buffer in the first video here. In the second video, we're going to talk about considerations in choosing a buffer system, and then in the third video, we'll choose a buffer system with a specific pH and talk about 3 different ways that you could make that depending on what's available. For right now, these are the questions we need to address. What is a buffer? What does it do? And how does it do it? And I think if you said to your typical high school science student, like somebody who's had a year of biology or chemistry taken care of, they'd probably say like a buffer is a solution that resists changes in pH. And that's true. That is what a buffer does. It resists changes in pH. And in the big picture, that's important for things like food preservatives or swimming pools or all kinds of other things. So that begs the question, what is a buffer? If it's not something that resists changes in pH, which it is, what is it really? And the reality is it's a solution with some mixture of a weak acid or base and its conjugate. Okay, I'm going to write weak acid, and I'll alternately put weak base and its conjugate. So we'll say and the conjugate base, or and the conjugate acid. All right, so that is the idea of what a buffer is. And I want to just glance real quickly at an example of like a weak acid and its conjugate base, and then a weak base and its conjugate acid. So, for instance, an example of a weak acid that takes very little writing is HF, hydrofluoric acid, and its corresponding conjugate base would be F minus. And we'll take a step backwards here and say, like, you can't just get F minus. You can't go to a chemical supply house and buy F minus, but what you can buy is some fluoride salt. A common example might be sodium fluoride, and that sodium is a spectator. It's not involved in the equilibrium system, but that's how it balances charge. So I guess one of the first ideas we need to consider is you can't purchase both of these things separately. One of them will probably be the salt version, and one of them will probably be a solution. In the example of our weak base and its conjugate acid, a weak base example might be ammonia, NH3, and its conjugate acid would be NH4 plus the ammonium polyatomic ion. And again, you don't buy ammonium, you'd probably get something like an ammonium chloride salt, so NH4Cl. Again, ammonium ion needs some anion to balance it out, and you've got electrolytes that dissociate to produce the species you need. So we know what a buffer does, we know what it is, and I want to talk about how it works. And the short answer of how it works is common ion effect. And I guess it would be good to explain how that is. And it happens because you have species present in your solution from both sides of an equilibrium expression. So this is the idea here. You have species from both sides of an equilibrium expression present. Species from both sides of an equilibrium expression. And what that means is there's a common ion effect resistance to shifts in either direction, all right? Changes to the equilibrium in either direction. So this resists shifts, right? Changes in either direction. All right? So I'm just going to write out the sample from up here very, very quickly so we can see how that goes, which is if we have this equilibrium system, HF, in water, the aqueous dissociation equation, we get H3O plus and F minus. With our K expression, Ka, H3O plus, F minus over HF. If you just start out with some amount of HF, there's very little resistance to a shift in this direction. Q is really far from K if we talk about it in terms of equilibrium. If you have just F minus, there's very little resistance to a shift in this direction. But common ion effect says you've got something here and you've got something here already. which means there's going to be more resistance to a shift in that direction. Q is closer to K and it's not as favorable. So when you have something on each side, that makes it more difficult to go in either direction. There's resistance to going in those directions. So how can we make a buffer, at least qualitatively? Well, we can, I guess we should say how to make. You can go brute force, which is my preference because it's the least thinking, which is you just take some weak acid or base and its conjugate salt and mix them in some ratio. So the first option here is to mix some weak acid or base with its conjugate salt. Right? And that gives us both sides of this equilibrium. And that's brute force, I would say. The more elegant way of doing it would be to start with all weak acid or all weak base, and then use a strong acid or base to shift, to do some stoichiometry and end up with things on both sides. So that would be our second scenario here. It would be to mix again. But in this case, we might mix, and I'll try and color code this a little better. All right, here we go. Mix excess weak base with some strong acid. Or the other option would be to mix excess weak acid with some strong base. And in both cases, what you're doing is taking your weak acid or your weak base, and you're reacting to convert some of it into its conjugate. We'll look at a couple quick examples with the HF of this scenario. And again, the idea is, if you have all this and you add some acid, you can turn some of your weak base into your weak acid, and it'll be easier to see with an example. So we'll look at our weak base, maybe something like the fluoride ion. So we'll have F minus, maybe from something like sodium fluoride or whatever. And we're going to put with it some strong acid like HCl. And I'm not really worried about the Cl because that's a spectator just like the sodium would be. So I'm just going to put the H plus. So if I take F minus with a strong acid, which is H plus, I end up making this weak acid HF. So as long as I start with a bunch of this and I use some but not all of it, I'll make some of this and have some of this left over. And I know that's kind of hand wavy, but we'll look at it with more clear examples and some numbers in a minute. But again, start with a bunch of this, use a little bit up, and you got a little bit of this that you've made. Now you've got things on both sides of our equilibrium expression. If we look at the reverse of that, our excess weak acid, the HF in this case, and you react it with something like sodium hydroxide, and again, that sodium would be a spectator ion. We have, I'm just going to put OH minus. We end up with water, and what's left is that F minus, our weak base. So similar to this, as long as I have more of this than I consume, I'll have some excess HF, some will be left over, and I will have made some F minus in the process. And then once again, I've got stuff that's on both sides of that equilibrium expression.